So here is some motivation. Here we'll start with this example we've talked about quite a few times now. Consider a beam on roller support and a pin joint. There is a load P. Clearly, because the load P, this beam is going to have stresses. I've hopefully convinced you that it'll lead to, if it needs to V and M, it'll lead to sigma and tau, right? And so when we are looking at a beam and trying to understand the stresses, we want to do that for each and every point on the beam to understand what is the critical point is, right? So that comes from the bending moment and shear force diagram. So bending moment diagram will give you M as a function of X, shear force will give you V as a function of X. That can be used to compute tau as a function of X and sigma as a function of X. So given that, we might be interested in knowing maybe what's the stress on that point. Okay, I'm going to blow that up. And maybe that point, well, we'll look at it in terms of a square. Now, as I told you, this will induce stresses, sigma x, sigma y, and then there would be tau xy, which is equal to tau yx, right? So that's like, I mean, that need not be, well, in this case, I'm just assuming that those are the stresses, but depending on where you choose the point, maybe you'll have tau, you may have sigma, you'll have both. We don't know, but in general, you'll have those three stresses. Now, when we do the shear force bending moment diagram, we'll only get those stresses in that particular rectangular plane stress element in that direction. But it may happen that there's another plane at which there's a normal stress is the highest. So maybe we want sigma tau in this direction. Okay, so this section makes an angle of theta. In other words, instead of computing it for an element in this fashion, we might be interested in a different kind of a section, which has a element this way. And then we are interested in computing sigma, I'll put x prime, sigma y prime, tau x y prime. We want to compute sigma x prime, sigma y prime, tau x y prime. And here we know we have computed sigma x, sigma y, tau x. So that's known, but we are not, after all, not interested in the way that particular plane stress element is, but we want it to be the stress in an element which is rotated. Why you want rotated is because the maximum stress, you've heard of principal stresses, those principal stresses, which are the maximum stresses which can act, need not act in a section which is along the xy direction. They may act at an angle to the xy direction, like this. Okay, and remember that when you do a design, you're interested in the worst possible stress, not the minimum possible stress or the average stress, the worst stress. And the worst stress might be in this section. Okay, so the worst case stress might be in a different direction. So if the worst case is in different direction, and if you do not identify it and don't use it for design, clearly that material will break at that worst case section. So you always have to figure that out. Now, why does this happen? Why do you have a worst case stress in a random direction? You might, for example, design a beam like this. You might take two beams and join them. So there's a weld here. Okay, that weld is probably a weakest link in the beam because you joined those materials together. So this is the weakest link. Weak here. And here you are clearly interested in the stresses in this direction, where the weld is, rather than having the stresses in the direction which is x and y. So this is clearly at an angle of theta, and you want to compute that stress in that angle. So that's the point of Mohrs circle. It will actually give you the stress. Okay, so the way that you think of this is like this: sigma x, sigma y. I want to know the stress, the shear stress here in that particular direction, and the normal stress, sigma, of course, this tau x, y. So these are unknowns. I want to compute those stresses, and I know these stresses. And of course, I also have given the angle theta. Okay, so that's the motivation. Let me write down one sentence about what Mohrs circle actually does. So if you know sigma x, sigma y, tau xy, the Mohrs circle is a way of computing sigma and tau at a given angle theta. So it gives you the transformation. Turns out that sigma is sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 times cosine 2 theta plus tau xy sine 2 theta, and tau is minus sigma x minus sigma y divided by 2 sine of 2 theta plus tau xy cosine 2 theta. I should also show this diagram, which I drew a while back. It is sigma x, sigma y, tau xy, the sigma, this is tau. Now this is assumed that you just cut the rectangle at a cross section at an angle theta. Okay, so when you think of the Mohrs circle, always think of this figure. You're given sigma x, or you know something about sigma x, sigma y, tau x, y, tau x, tau yx, which is same as tau xy, and you are told to compute sigma and tau. Given. And of course, you're also told something about the angle. It's the maxima, which would be when d square f dx square is less than 0, and minima if the d square f dx square is greater than 0. So we do something similar. So here what we're trying to do is compute theta for which sigma achieves max min value. And we do so By using this fact in calculus, we compute d sigma d theta, equate that to 0, and then second, we solve for theta. So when we do this calculation, d sigma d theta equals 0, we get the following equation for the angle. We get tangent of 2 theta, I'll call that theta p as the principal stress, direction of principal stress, as 2 tau xy divided by sigma x minus sigma y, where theta p is direction of the principal stress. Okay, let me actually call these, let's call this equation 1, equation 2, okay, and so when I do this, I'm actually using equation 1. Okay. So now what I'm going to do is I'm going to take, let's call this number 3. So now we'll do is we'll substitute 3 in 1 and 2. 1 being the formula for normal stress sigma, and 2 being the formula for tau, and solve for sigma AB. These are the principal stresses. It comes out to be sigma x plus sigma y divided by 2 plus or minus. So there are two principal stresses, sigma x minus sigma y whole thing square plus tau xy square. And then the shear stress comes out to be actually 0. Which means that there is a direction theta, theta p, where the principal stresses are non-zero. Okay, there's of course a special case when they could be 0, but typically non-zero, and then tau is equal to 0. Here sigma a, b are principal normal stresses. Okay, so we've computed the normal stresses. Now let's look at the shear stress, the maximum shear stress. That also can be obtained just like before. So what we did here is we computed the maximum principal stress by doing d sigma d theta equals 0. We'll do the same thing for tau. We'll do d tau d theta equals 0 to compute the maximum principal shear stress. So the second thing we're going to do is compute theta such that the shear stress tau achieves max or min. So for that, we do d tau d theta equals 0. And then second step is solve for theta. So if we do that, then we get the answer as 10 to theta s equals minus sigma x minus sigma y divided by 2 tau xy. Call this the fourth formula. This is the direction of maximum or minimum shear stress. Okay, and then the final thing is we substitute number 4 in the equation 1, which is for normal stress, and for 2, which is the shear stress, to get a formula for the principal shear stress that is going to be plus or minus. One of them, the plus sign could be is the maximum and the minus is the minimum. So we get sigma x minus sigma y square plus tau xy square. And then the corresponding shear stress, normal stress is sigma x plus sigma y divided by 2. Okay, so here it is. Okay, so I said more circle, but where exactly is the circle? So to show you where the circle comes from, let's look at these equations. I had two equations for the stress sigma and tau as a function of the angle theta, theta being the angle made with the rectangular section I assumed. Now what I'm going to do here is I'm going to move things around. I'm going to move this part to the right, or sorry, left, and then square things up. So let's do that. So this is motivation for the Mohrs circle, the circle part of it. Where does the circle come from? So from 1 and 2, I can write the equations as follows. Sigma minus sigma x plus sigma y divided by 2 equals sigma x minus sigma y divided by 2 times cosine of 2 theta plus tau xy sine 2 theta, and then tau equals minus sigma x minus sigma y divided by 2 sine 2 theta plus tau xy cosine 2 theta. So what I said is we're going to square the equations and add them up. Okay, so if you square the left-hand side, you get sigma x plus sigma y divided by 2. So this is squared plus tau squared. So everything on the left-hand side has been squared and summed. On the right side, if you sum it up, we'll square it and then sum it up, you will find that you end up with something like you have cosine square, sine square, but they all will sum up to 1. So you know that the identity sine square theta plus cos square theta is 1. You'll see it'll come out in that form, and you can try that by yourself. I won't spend time doing that, but the right-hand side gives you something which is not a function of theta anymore. So it comes out to be this sigma x minus sigma y square plus tau xy square. Okay, note that sigma x, sigma y, tau xy is given to you. We know the stress. So this thing here is an equation of a circle, right? Where so you think of it in terms of these axes. Say x, y, where x is sigma and y is tau. Then the center, if the center of the circle is sigma x plus sigma y divided by 2 comma 0. In a radius, which I would write down just a bit. The radius of this circle is sigma x minus sigma y divided by 2 square plus tau x y square. So if this is the center of the circle, xc, yc, so equal to xc, yc, then this equation can be rewritten as sigma minus, we just write it as xc, yc is fine, I think. Well, we can write it as, better way to write it would be sigma c 0. And then we have sigma c square plus tau square equals r square. So that is the equation of a circle, and that's where the Mohrs circle, the circle comes from. So as you rotate the rectangular, I talked about the small piece from that beam, you will see that the stresses, sigma and tau, lie on a circle. This circle is called a Mohrs circle. Yeah, I'm going to draw one. I'm going to dedicate one more page to the Mohrs circle. It turns out that all these calculations which I showed for tau, sigma, and so on can actually be conveniently extracted from the Mohrs circle without really writing on any of those formulas. There's some basic things you need to know, but once you know, for example, you know R and you know sigma C, you can pretty much get all these things just from that circle. You don't really have to write those formulas. So any problem in this section, you could do it entirely based on the formulas if you're a formula person. By formulas, I mean, for example, there's a formula for principal stress. right? You could use these formulas or these formulas, but you could also do the same thing entirely from the Mohrs circle. If you're a visual person, maybe you do it from Mohrs circle. If you're a more formulaic person, you could maybe use the equations. I'll do it both ways. But before that, let me write one. I'm going to tell you how those formulas map to this Mohrs circle so that you can actually use the Mohrs circle to do these calculations. Okay, I need to draw a really big circle for this. Okay, so as I said, x-axis is sigma, y-axis is tau. The middle of the circle is simply sigma x plus sigma y divided by 2, 0. Okay, and remember, everything here, what we have talked about, is tied to this rectangular, well, square element with stress sigma x sigma y and then there's shear stress tau xy is equal to tau yx. Okay, so once you have sigma x, sigma y, you take the mean, and then that's your center of the circle. Okay, now remember that when you have a problem, you typically know the value for sigma x, sigma y will be like 50 psi or 100 kilonewton per meter square. So you know the value of sigma x, sigma y, tau xy. So what you can do here is you can actually plot this value on the circle, because after all, this is a circle which is on the sigma tau axis. So take sigma x, let's say it's this point. Now there's a convention I'm going to use. I'm going to use a convention that for sigma, the convention is positive is tension, negative is compression, right? This is very clear. And for tau, the convention is going to be positive is clockwise and negative is counterclockwise. Okay, with that convention in mind, we have sigma x. This is positive the way it's shown. So I drew sigma x positive. And tau xy on this face, you can see that it is acting in the counterclockwise direction, right? So counterclockwise is negative. So I have to choose this to be, this is going to be minus tau xy. So this point here is sigma x minus tau xy. Similarly, y is again tension. So let's say that this point is here. Since the stress here, shear stress is acting in the clockwise direction and clockwise is positive, I need to show it up here and not down. That I have an option of choosing this point to be here too. I choose it here because it's positive tau. And let me connect these 2 points by a straight line. Now they have to be the way I've shown because this is tau xy and this is minus tau xy. So they have to basically be ends of the diameter of the circle. Okay, so here we have sigma y tau xy minus tau xy. Okay, so what is missing in this is probably the radius. So the radius is the radius is right here, r. Okay, now it's not hard to see that if you want to compute r, all you need to do is just do sigma x minus sigma x plus sigma y divided by 2 square plus tau x y minus 0 square. How do you compute the distance? You'd have the coordinates of the endpoints, right? You have the coordinates of this endpoint, just can take the Euclidean norm, which is subtract them and they take the square, and that you have the radius. So you don't really need to use that formula. You could just use it. You could also find the radius this way from this point to this point using the same formula, the Euclidean distance formula. Okay, so that's one thing. Now, what about the principal stresses? So by the way, this is easy. This is easy. I told you how to do that. Let's see how to compute the principal stresses. The principal stresses are, let's go back to this formula. This is the principal stresses, sigma A, sigma B. You see that they have a coordinate of tau equals 0. So they have to be the endpoints of that circle when it meets the sigma axis, right? Tau is 0. So we can go back and notice that these points have tau equals 0. So this should be sigma A comma 0. And this is sigma B comma 0. So once you have the circle, it's very easy to compute that point. Okay, then let's see how to compute the shear stress. So the maximum shear stress, tau AB, has an x coordinate or a sigma coordinate of sigma x plus sigma y divided by 2. But what is sigma x plus sigma y divided by 2? That's the center of the circle, right? So go back, it's this point. So the maximum principal shear stress has to be right this point. Tau A tau B. Okay, again, easy to compute that once you have the circle. Okay, what else is missing? Well, we're missing the direction. Now we have the direction. This is the direction of the maximum principal stress. So how do we plot that? Well, if you look at, well, if you see this, it's the angle made by this stress. Well, let's look at the other one first. Let's look at this one first. So this is the stress for the maximum stress sigma A, sigma B. So this is the angle made between sigma x, sigma y, and another plane where the principal stress is sigma A, sigma B, and 0 for the shear stress. So it's basically the angle by which you need to rotate this, theta. So that actually can be computed here. It is essentially this angle. This angle is 2 theta s. This angle made by the given stress from the sigma axis. And then there's a similar one for the maximum shear stress. This one's the maximum shear stress. So this angle is when tau AB is the max value, sigma achieves a value of sigma x plus sigma y by 2. So that should be clearly this point. So it's the angle is going to be this from here all the way. This is 2 theta p. So you can link this back to this rectangular element. It is this angle we were after, theta s. So if you rotate that plane element by an angle of theta s, you'll see that it'll have the maximum principal stresses, sigma A, sigma B. Okay. There's another interesting thing, which you can easily see from this figure. This is the direction of the maximum principal normal stress. This is the direction of the maximum principal shear stress. This angle is 90 degrees. It's always true that the principal stresses make an angle of 90 degrees with each other, no matter what. Okay, the other key takeaway point from this figure is that each point on the Mohrs circle corresponds to an orientation. So when we had this point, it was this orientation for the rectangular element. When we looked at theta s, it's basically this rectangular element rotated by an angle of theta s. So when you rotate it by theta s, this corresponds to sigma A, sigma A, sigma B, sigma B, and then the shear stress is 0. If you further rotate by theta P from this orientation, then you'll get the principal stress in the shear direction. So the key takeaway here is that each point on the Mohrs circle, each point on the Mohrs circle corresponds to an orientation of the stress element, the stress element being this square, which we've shown so many times here.